So I'm very happy to be here, very excited to kind of open a new chapter in our collaborations as well. So indeed, as Musard mentioned, I'm based at Chalmers, but since recently, I'm also visiting professor here at KTH. Some of the collaborations we're already doing, but this unlocks even more collaborations. So I'm very much open to how we can set this up in terms of projects, supervisions, mentorships, all kinds of initiatives. So yeah, definitely very exciting to start in this role. And the talk today is about the general area of web crawling and security scanning. This is an area that we've been pushing on recently and have some nice results to share. So essentially, yeah, meeting the challenges of today's web, how to kind of crawl it in depth and how to find vulnerabilities in web applications. That's the goal today. So you had a kind of, yeah, as I said, it's a line of work we've been pushing. And today I'll talk about a selection of 3 particular stories from this line of work, as also published recently in 3 papers. Coincidentally, these are the top 3 venues in all of security. So that's kind of nice feature of that. Security and privacy, CCS, and Usenet security, where you publish them. So with the goal of first introducing kind of the foundation for this kind of crawling and security scanning. This is the work on Black Widow. That's the first part. And then talking about 2 separate kind of areas of focus. One is what challenges we can meet on the client side. So, and the second paper here about Black Ostrich. And then the third story will be about the most recent paper we got published in Usenet this year about going into the server side. Okay, so foundation web crawling, challenges on client side, how do we explore the state on the client side, and then how do we explore things on the server side. So all these things together will make into this larger story. So that's the plan for today. And I should mention that if you were here a year ago, so it was a talk that I was giving, and there I was very much going into the second part. So this time I'll try to maybe focus on the other parts more, but I'll mention the second part as well, which some of you will recognize. Okay, so right, the general area here is that does not really need motivation, but just to remind you that it's challenging to find problems in web applications, and there's a lot of is at stake in web security. So a couple of reminders here is the Equifax data breach when 150 million people's data was breached because of web application vulnerability. And Equifax, so one of the biggest banks in the US. Another example that also you've seen on the news is Cambridge Analytica. So another example of security vulnerability that has led to dramatic impact with millions of people affected and information being harvested through insecure APIs. Okay, so yeah, this is a very active area. A lot of things happen every day. There's news of new attacks. And it's costly both in terms of actually, handling these attacks, incident response, fixing things, but also, yeah, costly in other ways. So one way to measure is kind of how much bounties is being paid by major players of the web. And if you just look at 2022, then so Google has paid out in 12 million, and Meta paid 2 million in bounty just that year. Right, so basically showing extent of bugs being found every day, and it's in mostly web-based products of these companies. And what is important for this talk is that a large fraction of these attacks is cross-site scripting attacks. Okay, so that we can see both because it's for 20 years it's been in OWASP top 10. This is a classification of attacks in the web community. And also, if you look at reports by HackerOne, other bounty platforms, they're kind of largely dominated by these kind of cross-site scripting attacks. So a lot of attacks being found and found, and vulnerabilities being found, and a lot of insecure software having those kind of vulnerabilities. So obviously an important topic for us to focus on. At the very high level, okay, what are these type of vulnerabilities? What are they? Well, kind of usually it's about some kind of code injection so that the attacker tricks the application to run the attacker's code. So here you have a typical interaction on the web. The user visits a website, social.com, and then essentially maybe posts a comment, and then views the comments posted so far. So what can happen is that if the user is malicious, the user may try to plant a malicious comment here. So instead of providing a text, the user puts a piece of code, okay, in this discussion board. And then essentially when the next user comes, the user retrieves the content of the blog, and then the attacker's code will be executed and run in the browser of the user. Okay, in this case, what we achieve is alert 1, but of course, yeah, what we can run here is arbitrary code, can exfiltrate user credentials, can deface the website. So this is all kinds of confidentiality and integrity attacks can take place. So in a nutshell, that's the cross-site scripting for the purpose of this talk. You can already see that this is a stored version of cross-site scripting. So it's a bit trickier than just bouncing back the code. So because there's an intermediate storage. So as the attacker interacted with social.com, actually the code has been stored in the database. So there are a few steps here. We need to deal with client, we need to deal with the server, and we need to deal with the database before the code reaches the victim. Okay, so simple, but already we see that there's some intricacies we need to handle. So there are frameworks and there are solutions to sanitize this kind of input that is not trusted. So for example, if we look at this blog, then we might want to escape the characters so that the text the attacker plans is not run as a code, but interpreted indeed as text. So that's the kind of the ultimate goal for solving this. So from a solution point of view, yeah, there are frameworks, there are ways to solve this. But the hardest part really is to find when this is missed, because potential for injection can be in many different places. So we need to, in this example, without comments, but this could be somewhere deep in the web application, some admin panel, or some newsletter email that people can potentially click on. All kinds of, as you get your news, you probably noticed that all kinds of tracking links are inserted in newsletters. So that's a perfect way to deliver process scripting and access payloads. So many things to look for. And in fact, so I mentioned some numbers that these attacks are present. And one interesting example is Google Maps that people use every day. And you would think, okay, this is a super scrutinized web page. In fact, well, even Google Maps has history of cross-site scripting attacks. So yeah, that's where our research comes into the picture. This is the streak of approaches and tools: Black Widow, Black Ostrich, and Spider's Hand. Essentially, it's all about detecting vulnerabilities that are based on cross-site scripting. So let me start with Black Widow because it sets the foundation of what we're doing. So we need to deal with complex web applications. I mentioned Google Maps, so this is a great example. There's a lot of interaction in there. There's a lot of code, both on server side, client side. There's a database involved. A lot of that code is actually from third parties, so there's very little control over that. And essentially, yeah, that makes it hard to find vulnerabilities. So at a high level, we can approach this by so-called white box and black box types of analysis, where with white box, actually you would have some source code of the application, maybe you use some of that knowledge. Unfortunately, in many cases, it's not available. And what I mentioned with third-party code, well, if you load a JavaScript library on the client side, then you don't even know what this library will be at the time of execution. So essentially, no chance we can do anything here because we simply don't have the code. So therefore, in our work, we go for black box. So trying to stick as close as possible to what the application actually is doing. And therefore, we get all the dynamicism to deal with, but then we also get very direct approach, in terms of tracking attacks. So yeah, that's why all of the scanners I talk about today are black box with a little bit of grayish box component of the last one, but that's kind of the idea. So here's an example to illustrate the complexity of flows that we have in web applications today. So this is some kind of service where we have admin that can register users and can view users. And the nodes here essentially correspond to URLs in the web application through which you can navigate. The interesting thing here is that we can jump from one state to another in the application by doing different kind of actions. Okay, so it's not the style of a classical old web where we navigate through static links. In fact, the behavior that we are exercising here is quite dynamic. Okay, suppose we start with index PHP. Then we click on the link. As if say we're an admin, we want to kind of log in. So we need to go to the login part of the application. Next thing is submitting a form. Okay, it's not a link. Actually, we need to provide the input. So that's a challenge for an automatic scanner. How do we even provide the right input there? Okay, so we log in. We go to the admin part, and there we click. There's no link, but you can click on an area in the web page, or sort of kind of on a pop-up, and end up in admin users parts, and that's where you can add users. Okay, that's the kind of that's how you kind of add users in this application. So here there's a potential. So deep inside of this flow, there's a potential to get a malicious string, malicious input, which ends up somewhere that is not visible right away, because here we can only add users. We are still in this adding user, and only when we go back to index and then view users, only then actually we are getting exposed, and the payload that we planted is reflected back to us. Okay, so we inject in one place, but it's in the output in the other place of application. So this is a illustration of a non-trivial data flow that we need to track if you would want to have automatic analysis of this. So yeah, essentially, if we are to create a scanner, somehow what we would like to achieve is that we'll be able to track, even though these are links, forms, and clicks, all of that should be a way to kind of take into account as edges in our model of the web application. And then, as we plant the user, we should be able to somehow mark, the input, and look for that mark later on, right? So basically, so this is the kind of challenge that we need to resolve: navigation, traversal, and non-trivial kind of data analysis. Okay, so that's the challenge that we are solving here with our approach called Black Widow. Yeah, so to go through these challenges, okay, so navigation, as I mentioned, so how do we represent all ways to navigate as edges in our navigation graph? So previous work has only addressed this partly. Traversing, so how do we decide how to explore our application? So one interesting example could be calendar, where you click next week, okay, you get another page, maybe even a different URL, so you can keep clicking on, and then you get more and more of the navigation graph, and there's no way you can cover it because it is only graphs all the time. So we need to kind of worry about that. And the interested dependencies, okay, how do we make sure that, so this, when we have an injection in one state and result of injection being triggered in another state. So how do we combine that? So these are the three big challenges. And interestingly, when we started looking in this area, so we saw like different efforts addressing these challenges separately. In crawler called Jack, it was all about user events and asynchrony on the browser. Enemy of the state was all about server-side state, not so much about client-side. And also we saw some, reverse engineering, trying to kind of understand web applications by reverse engineering. So in our approach, we are combining all of this and essentially making the connection that well, if there's some exploration on server side and there's some on client side, we really want to put it together as a part of the kind of navigation model. Because, yeah, I mean, that's how web application works. It combines the client and server side. We cannot create them separately. Okay, so that's the key idea. And now nodes are client-side states, not only server sides. And indeed, so what we represent in our navigation model is, yeah, all kinds of events, including links, form submission. Yeah, and that's something that previous crawlers couldn't handle so well. And also, yeah, user events like clicks. So that, yeah, essentially we pretend we are users when we browse the web. For traversing, okay, so essentially, yeah, now that we have the graph, how do we traverse it? Well, essentially we kind of, yeah, do a breadth first search, right, when we're kind of exploring the graph, with a particular attention to forms, because those can be tricky to pass. Sometimes you need to find the right input. For example, login, if you just randomly select input, well, you will not get far. So we need to kind of essentially get our crawler to be able to auto-register and auto-log in so that we can make interesting progress, not just get stuck here. And also we need to have yeah, a model about, you know, not just kind of simple search, but driven by the requests that are potentially unsafe in a sense of, you know, actually having side effects. For example, if it's a get request, okay, then we safely move to this state. So nothing dynamic happens here. It's only from here. Therefore, the kind of backtracking that we need to do is up to the safe state, up to the get. So from here on, so dynamic things can happen. Therefore, we might need to backtrack. But we have some kind of constraints on how far we need to backtrack, because up to a certain points, actually, we have quite static behavior of the application. So that's part of the traversing challenges. Okay, so that way we can explore and get to the interesting parts. And now, finally, for data dependencies, well, so here the idea is that because we're in a black box setting, so one way to do is kind of end-to-end taint tracking is to essentially plant a random token somewhere in the application and then look for this token as you continue browsing, right? So this is a work that, yeah, this works very well because essentially now we can capture interstate dependencies by planting the token once we're in the add users part. Plant the random token, and then as we get to the view users later on, the crawler discovers, oh, here's this random token in right here in this output that we generated here, so we can make the connection with where it was injected and identify this interstate dependency. Okay, so that's a nice feature, and you can already see here that yeah, this deals nicely with stored injection, because, well, if we use the database when we add users, okay, that's great, because then the taint will propagate into the database and will be retrieved and used in the yeah, when we view the users. Okay, so then we'll find it there. Okay, so yeah, so that's essentially, yeah, the three pillars of crawling, combining the different crawlers we did it before, putting it all together, and full automating. So that's the result is essentially a push button tool. Just give it the URL, it starts a scan, and we've done it successfully on large applications like Amazon, for example. So it's yeah, and what we've seen in evaluation, so it does work very well. Essentially, we've taken a bunch of state-of-the-art crawlers. So I mentioned some of them that, yeah, that's like partial addressing of the challenges before. And then we essentially took two types of applications. Reference applications used in this area to compare, you know, yeah, the effectiveness of the scanners. So they have intentional vulnerabilities. Well, most of them intentional vulnerabilities. You know, some people discover new ones that were not intended. And then a bunch of production software like osCommerce and PrestaShop, where there's not supposed to be any vulnerability. So we've looked at both, and essentially, yeah, the kind of results that we arrive at is essentially, we pair our crawler with every other crawler in this dimension here, and then we use all the different applications for comparing the crawlers. So that way we can show what's the percentage of lines of code we can cover on server side compared to, in this case, enemy of the state. So what's the percentage that only we can cover? What's the percentage that is common that both can cover? And what's the percentage that only enemy of the state can cover, right? So this is the kind of interesting number for each crawler and each application. So with that, we get a quite nice picture. So all the blue stuff here you see, it's this is unique to Black Widow. So only we can cover those lines of code. So yeah, it's kind of largely dominating the others. And on average, it's improvement from 63 to up to 180%. So clearly we can see much more of the web application. So what we are measuring here is lines of code on server side, right? So this is the interesting part because that's where their vulnerabilities are. Okay, so that's great. And in terms of vulnerabilities, so so the data flow analysis I mentioned is looking for vulnerabilities. So this is the cross-site scripting vulnerabilities that we're after. Essentially, here we have the different scanners, and this is the reference implementations. So we find more than others here, and for the modern ones, we're able to find cross-site scripting, but no other. I mean, basically, the others cannot find any new ones. But we managed to find both reflected and stored cross-site scripting. So yeah, this does push the boundaries of what we can achieve with black box map scanning. So some of these vulnerabilities were in software like HotCRP. So we have acknowledgements from HotCRP that patches based on our reports, and also we got some CVEs from some of the other ones. So that's great. So yeah, I mentioned this is really a push button approach. And a beautiful kind of feature is that there are no false positive, in the sense that the crawler is able to validate any kind of potential cross-site scripting because we are dynamic, and because we have the we have the whole execution that we are monitoring. So we are able to inject the payload and see where it shows up, and verifying that actually we got a unique XSS that is being run. So we are able to kind of demonstrate exploitability by the crawler itself, and that's what really is a appealing thing. And compared to static analysis, where we usually fight with false positives, here the beautiful kind of feature is that here by design we don't have any false positives. So so that's great. Okay, so yeah, we're building this foundation for crawling, but so essentially there are kind of two parts that remain open here. So we focused on navigation modeling, traversing, and interstate dependencies. Here, essentially, even with this addressed by Black Widow, we essentially, when it comes to providing the right input, still kind of unclear just from appearance of a web page to decide which input should be the right one. What happens in the classical scanners is that they try to fuzz inputs and provide like a dictionary of known inputs. Okay, if it looks like an email, or like there's an email in the ID, then the scanner would try to give an email, right? So this kind of heuristics. But the problem is that often, you need data of certain format. You need phone numbers, zip codes, and then these kind of crawlers, they get stuck. So so the problem of finding the right input still remains with Black Widow. And that brings us to the second part of the story with exploration of client side, right? So getting input validation checks resolved. So and here's an example of where this can be a problem. Okay, so let me show you a page. See if you can get it. Show, it's fine. Okay, so this is one of the pages from our data set that we were crawling. And so here you see that if you're just fuzzing an application with a black box approach, okay, you might kind of provide some input here. Actually, it's accepted, right? But then you kind of provide another one, and then you get stuck because there's a requirement that this has to be valid input. Okay, so this is where all the crawlers get stuck already, potentially, because essentially the web application requires that this is a valid email. Okay, so actually, if you look at exactly what happens here, let's inspect the element. So we'll find that indeed, so this is where I might need to increase. So indeed, this is an input element, email address. Okay, and essentially what is required here to pass this input validation check is that we satisfy the attribute called pattern, and the pattern is the regular expression. Okay, so you see the regular expression itself. Okay, well, essentially it's actually it's quite liberal once you look at it. It says that a bunch of no at signs, and then at sign, and a bunch of other no at signs, dot, and then a character, either lowercase or uppercase, between 2 and 6 letters long. Okay, so actually, web application tells us already what the expected input is. So that's cool if we are automatic crawler. Then, of course, we can do something like this. Okay, that's accepted because the check is done by the browser based on this pattern. Okay, so that's great. So then the idea is that can we use this knowledge to drive the scanner and provide this kind of input? Okay, so that's one thing that we'll be pushing. And then the other thing that we are pushing also is, well, now that we are playing with this input, why not also trying it for XSS payloads? Okay, so this is the second application. And as we saw this with a pattern, well, it's quite a liberal one. So if I try something like this, then as long as there's that's a sign in the right place, and then hopefully it's accepted, right? So something like this, yes, it allows me to go to the next element. So essentially the client-side check is happy with this input. So, and that's of course, potentially problematic because if the server side is doing the same thing, then there's a vulnerability. Okay, so that demonstrates, the challenge. And so, what we saw is HTML pattern with a regular expression. You can see how these expressions typically look like. The one we've seen is very much in this style, quite liberal. And therefore, so this would be rejected because there was no at sign. This will be accepted. And as we saw, this is also accepted. Okay, so based on this, essentially what we are doing is trying to look for regular expressions on web pages and trying to solve them using SMT solving techniques. So that's the kind of second part of the talk. What we immediately run into is that regular expressions on the web are not textbook. So they're quite a bit more complex. This is a standard expression used for passwords. Okay, so let's, those of you who know regular expressions can understand this one. Otherwise, you can look at this picture saying that, well, this part is a bunch of digits, right? This is called positive look ahead. So we don't consume any of the regular expression. We just check the condition that essentially there should be some at least one digit, right? So at least one digit should be part of it in this expression. That's what this part does. Okay, then at least one lowercase letter, at least one uppercase, and should be no white spaces in the password. Okay, other than that, it can be any string. And that's the part here, any string is accepted. Okay, so, well, if you just give this, I mean, currently there's no technology before our work, there's no technology to solve this automatically because it has features like look aheads, which state-of-the-art string solving couldn't solve. But that's where we essentially, develop that part to make sure that for the practical regular expressions, we can leverage SMT solving it. and solve those expressions. Yeah, one interesting aspect is that, what if we solve this on the client side? What about server side? Because it might be that we don't have any constraints on client side, but on server side, we actually check input validation. Well, it turns out that the client side actually gives a very good heuristics about what's happening on the server side. And in fact, in some frameworks like Spring MVC or ASP.NET, essentially, there's already a mechanism of reusing the same pattern on server side and the client side. So if you're solving the one on the client side, then you also solve it on the server side. Okay, so that's great because then we use the knowledge from here to pass input validation checks here. So yeah, in this example, see that, okay, there's some movie database, and then there's some genre, and then there's some kind of conditions of what the genre can be. And that's exactly the regular expression that okay, that's great. So then essentially we use SMT for two problems. So given the regular expression, what's an input so that I can make progress in the application? And the second question we can ask, what's given a regular expression? Give me an input that also contains a payload or XSS, right? So that I can use that in the scanner. Okay, so yeah, so to support those, yeah, we use pipeline of tools that does conversions of a regular expression to a format that we can actually digest and use in an SMT solver. And just to give you, yeah, so there's a long number of steps. And the crucial notion here is two-way alternating automata. Two-way in the sense that you need to move both, forwards and backwards, because we can have both positives. Well, we can have look aheads, but also look behinds. So the automata kind of needs to go both ways. And also, it's alternating because we need both existential and universal quantifiers in the automata. And let me illustrate the quantification part on the example of the password. Okay, so essentially, yeah, we show how we convert the regex into an automata, this form. So there are a bunch of look aheads, and each look ahead essentially corresponds to a branch in the automata. So this one was about a digit, right? We just encoded this by this, a bunch of everything, one digit, and then we are in the end state. Okay, so that takes care of this. Then lowercase ladder, uppercase ladder, no space. Okay, yeah, so here it's different, right? So basically, we're already in the end state, and if there's a space, okay, then we cannot accept this word anymore. So all of this are kind of existential traces in a sense, right? So kind of, it's enough to have one path to kind of show validity. But then because of, this is the last part is just all symbols. But then the universal part, comes from this basically, right? Because there are a bunch of look-aheads applied to the same regex. Therefore, we have the universal quantification here saying that, well, to accept the word, we need to accept it in all of the branches. Okay, and that's the alternating part. Now here we require the universal quantification over all branches from that state. So yeah, that works very nicely in practice. So essentially, I'll show the coverage we can improve. And in fact, not only for pattern attribute, where we have readily available regex, also you can use other HTML attributes like type and minimum and maximum. So from this, we can, for example, if type is email, okay, then really there's a regular expression that corresponds to email. We can use that in SMT. If there's minimum length, well, we use the minimal value in the input. So yeah, we can support all of that, and also some of JavaScript-based validation, because much of that is using regular expressions. So we can rewrite the test method here, and essentially, as we crawl, when we perform the test, we pull out the regular expression and use it in SMT. Okay, so all of that is nicely compatible with our tool. So yeah, and essentially, then we can unleash it and use it on the web. So we've done two types of evaluation. So one is to harvest all kind of regular expressions used on the web. For that, we use both Tranco, which is popular web pages, and Common Crawl, which is largest internet archive. So we can gather patterns at scale. So of course, we can only, our scanner is active. We cannot unleash on live pages unless we have permission. Therefore, we create a test bed with these patterns in our own websites, so we can test and focus on the patterns themselves. And then we have second part of evaluation is open source applications where we can unleash the scanner. So in terms of coverage, so we get a massive improvement here. So essentially we take from the patterns we find, 99% are solved by our method, whereas other scanners are average on 36%. So that's quite a difference. The kind of patterns that we find and others don't. So this will be the passwords. This kind of various password-based regular expressions that we can solve and others cannot. Whenever there's a hard limit or like exact constraint on number of input, that's a perfect case for us, because for SMT it's kind of trivial regex to solve, and for a guessing scanner, of course, they would have no way to identify that. So these are all the cases that we can solve and nobody else can solve. More regular expressions like that, particular ranges, plus 49 or dot franz. We see many of these expressions. So knowing them and using an SMT can give us an input, but the general fuzzer wouldn't have any way to solve that. Okay, so that's great. What about vulnerabilities? So here, again, this is a testbed experiment. We look for vulnerabilities in the patterns that we find. And so again, we find, essentially many more than others in terms of vulnerabilities. So it's, compared to others, it's 52% improvement in number of vulnerabilities found. There was some interesting kind of false positives, if you like, for tools like enemy of the state and ZAP, because what they consider to be payload is this short strings, which just demonstrate, this dangerous characters are not escape. So for them, that's already an XSS. We argue that, maybe this is quite a short XSS, and if the actual pattern has a limit on size, this will not be exploitable. Okay, that's how they get higher numbers. Okay, but still, so still we can outperform. Yes, and these are the example that are all accessible and only we can find, and no other scanners. And there you have, so anything followed by friends or something that contains Instagram, well, the other scanners use that. Okay, so looking at top websites, so it was interesting to see, what kind of input validation they do. So in this experiment, we'll look at 100 websites that actually have some form of input validation. Then we do some crawling, and then we look what actually they do for input validation. Turns out that most of them use JavaScript-based, using the test in JavaScript, regular expression object. Some cases match. Pattern was found in 3 websites. Well, we still thought it was great to see some of that being used. Essentially, we can support 86 out of this 100. So that's great. But we also saw some challenges when the input validation was slightly spread around in the code. For example, one part would check the length, and the other, check some kind of pattern in it. So that will be very challenging for us without doing symbolic execution to put it into the SMT solver. Okay, but it's interesting challenges on which we are working now in the current work. Also in the real applications that use input validation. So these are open source ones, so we can tag them. In the application called Alex, which is about learning automata, essentially you can register a URL, and that includes a regex that you need to provide. So essentially, we can get much deeper coverage than the others. So yeah, we can find all the URLs of the application. The other ones get stuck in creating a new project. Helping Hands is kind of a web application for helping NGOs and companies. Essentially, we can make much bigger progress because they ask for a phone number that the other scanners don't get stuck at. And with application that manipulates DNS, so then definitely there's no chance for other scanners to get through that, because we talk about regular expressions that correspond to DNS addresses, and that's not in the fuzzing libraries of the current scanners. So yeah, this shows a very nice impact of Black Ostrich. Okay, so right, so now that we addressed the client-side challenge, okay, are we kind of done now that we can interact with the web application? So is this kind of challenge resolved? Okay, so well, not entirely, and that brings me to the third part of the talk. So essentially, if you look at the flow of information in a stored XSS, we start with input source, right? So this could be user input or comment or one of those emails that you click on. Okay, then for a stored XSS to work, you need to store kind of this input in a database. And then as you process the database, you kind of miss sanitization and output the payload in the HTML, right? Which will contain the code. So this is, on a high level, that's how it looks like. And so, yeah, okay. The secure way to do it is actually to do both input kind of validation and sanitization, but in some sense, you don't want to be too aggressive. You want to store as kind of faithful data as possible in database. So, because yeah, depending on the context, you might need this data. So, but at least you prevent obvious attacks here to some kind of obvious validation. Store the output here, store the data here. And then crucially, as you process this data, then you make sure that you don't turn data into code, right? When you kind of compile the output of your application. So when you're generating HTML, JavaScript, right? So here, this is very important where you do sanitization. So very often, the source of the problem with process scripting is here, right? It's this part, when you can accidentally turn data into code. So we call this unprotected output, right? So essentially you forget to protect output, and then you might have script string in your database. Now it's weaponized by becoming JavaScript. From a string in database, it becomes code. So it's here, right? But well, if you're doing black box scanning, well, actually, just to get there, we need to jump through a lot of hoops, and that we saw already with input validation. You need to log in, you need to provide phone number, zip code, and that, as we saw already, was quite challenging. So just to get to the state when database is populated in a meaningful way is already a huge challenge. Okay, so yeah, in some sense, that's very unsatisfactory or unsatisfying, because the problem is here, but to get there, I need to do a lot of work. Just not security related, just exploration related. Okay, yeah. So let's call this source flow, the part of flow between the source and the database. And then the second part of the flow is called sync flow, from the database to the sync. So in some sense, yeah, all flows, they have two parts. And our insight here is that a black box scanner actually, to discover this, which is very deep in the output generation part, we need to both discover source flow, sync flow, and put them together and actually relate them, right? So that it all becomes part of the sync flow. So the question is, well, yeah, I mean, maybe it's too much to ask. So how about, instead of going for the whole thing, how about we basically cut the problem into halves and only go for the second part of the problem, okay? And that only the interesting kind of flows in the first place. And that brings us to Spider Sense, the gray box approach, which also builds on Black Widow. Okay, so what happens here? Essentially, rather than fuzzing and exploring, the inputs of the application, you go straight into the database and do the fuzzing at database level. Okay. So, and by fuzzing, I mean, well, essentially some kind of light modifications. Typically, it's enough to modify a cell to see, the dependency, what this affects in the web application. Okay, and for validating that there's an attack, of course, you could also inject payloads and see where they show up. Okay, so if you can do that, partly, leveraging, recent progress on fuzzing. So there's a lot of, things going on in fuzzing, how to do it in a way so you don't break things. Here we need to be, a little bit careful because, breaking the web application is different from breaking, the program, standalone program. So, but in some sense, we have some nice heuristics here because we can look at URL space of the web application and see, do our mutations change that or not? So we have a way to detect essentially breakage of web application in a nice way, right? So staying in the web level. So if you do this, we fuzz the database level, we kind of, massage the cells. Then we end up with an approach that is still black box for the application. And the only thing that we touch is the database, right? So we know the structure of the database. We're free to play with that, but we don't actually touch the code itself. So with this approach, essentially, we can find, first we can find dependencies. And this is from a case study we've done, one of the best applications, one of the open source applications, where we can map the columns in the database with URLs in the website. So, for example, there's some kind of gallery URL. Oh, it will be rendered to this web page. Therefore, is a direct link, direct flow from this URL to the web page. Similarly, like this, and see, like the black arrows correspond to dependencies, and the red ones correspond to XSS because those are not sanitized properly. So but what we essentially detect right away is what we call code smells. And this is where the spider sense analogy comes in, where essentially, if there's something from the database that is pushed to the output without being sanitized, okay, that's potentially problematic. Okay, so this is very much, it smells like stored XSS. What this gives us, a lot of coverage this way. So lots of vulnerabilities this way. And actually, what also comes out of this is a nice study of, the types of vulnerabilities. Because starting from this, we can also check their exploitability. Some of them are just smells in the sense that we didn't find a way to exercise them. So there was no input we could find that would trigger, this vulnerability. We still argue they're bad because it's unsanitized output. So, but some cases we couldn't show that they're exploitable. In many cases, in fact, we demonstrated the full exploitability. So remember that, we cut the problem into halves. We have the automatic solution for the second half, but for the first half. So once we have the smell, so then essentially we do manual checking, how to get to that, who is modifying that, column in a database. So this part is manual. But a really nice example that came out of this work is what we called dormant XSS. So essentially, it's a vulnerability in WordPress, which essentially, so it was an output that was not protected, right? So this is a flow, exactly this type of flow. In the vanilla WordPress, it was not exploitable. So it was kind of in a part of WordPress that was not really called from anywhere. But essentially, if you install a WordPress plugin, then it kind of unlocks this vulnerability and makes it fully exploitable. Okay, and that's a great kind of lesson because having this kind of dormant XSSs and code smells is no good because if one day you extend your application, for example, by a WordPress plugin, then it might kind of trigger those vulnerabilities that are there. Now they become reachable, and that's exactly what happened with this case that we found. Okay, so essentially, that's the story of these 3 chapters in crawling and scanning. So super nice area. Very much invite everybody to work in this. A lot of open problems, and as you saw, there's some connections with SMT solving, with fuzzing. So all your favorite techniques can be applied here, I'm sure. So essentially, yeah, we've seen that securing web applications is hard and scanning is challenging, but we have foundation for scanning in the sense of putting together the pillars of navigation modeling, traversing, and data state dependencies. So with that in place, provided in Black Widow, we can build on this and grow it in different directions. So yeah, this solves kind of the navigation modeling problem. So that's very nice to solve before you start adding new components. Indeed, in Black Ostrich, we focused on source flows. Okay, how to get input, to match input validation, how to make progress in the web application quite successfully. And in SpiderSense, we were able to look at sync flows and protected output from the database to the application and found problems there. So yeah, increased coverage, a bunch of vulnerabilities compared to others. So yes, very much invite you to try the tools and think of how your tools can be, how your approaches can be useful for this area. So, yeah, thanks very much.